Now let us move further with the other topic of graphs. Now, there are certain terms and definitions we need to know about graphs. I mean, the because that's going to help us in future topics. Now, we already know graph. Graph is a set of vertices and set of edges. There is another term known as subgraph. Subgraph is nothing but it is also a graph with set of edges and set of vertices and set of edges. But the set of vertices is a subset of the original graph, set of vertices of original graph. And set of edges of a subgraph is also a subset of set of edges of the original graph. So if you look at this graph on the left hand side, this is a graph, and if we remove these, I mean if we take this part from vertex 3, 6, 7 and 8 and this bit on the graph on the right side, it's nothing but it's a subgraph of this graph on the left side, because the set of vertices are subset as well as set of edges is also subset of the graph on the left side. Then let us talk about connected components. Now, I'm just trying to create a subgraph of the graph on the left side, that is A till F vertices and its edges. And here on the right left side, what I have is 3 vertices with its edges. Now, if I can go on expanding this, and then let us stop at this part. So I have from this graph, I have picked up 4 vertices and its corresponding edges. And those edges vertex are part of are subset of the original graph that is on the left side. So this is also this graph on the left hand side is also a subgraph of the graph on the right side. Now, why we have talked about subgraphs? Because there is an important thing in graph, and this is the theoretical part. There is, I mean, we will not be looking at any algorithm here, but it's a theoretical terms which we need to know, and several times they have been asked in the exam that what are the connected components, or what are strongly connected graphs. Well, so those things they have asked, what is an articulation point, that which we are going to see later. So as part of the theory, we have to know about these terms. Now, why we have seen subgraphs? Because a part of a graph is a subgraph. And in this case, if you see, if I just consider E, F, and G of this whole graph, that will be a subgraph. Now, connected components are nothing but connected subgraphs. So, connected components are connected subgraphs. For example, here, if you see this edge, which is connecting vertex C to vertex E, this is the only edge which is connecting. It's connecting 2 components actually. If I remove this edge from C to E, there will be 2 subgraphs. There will be 2 components of the same graph if that edge is removed. So because of that edge, these 2 are connected components of the graph. Then how do we know that they are connected components or not? That the graph has a connected, that is, all the vertices are connected or not. How do we know? Now, we can perform breadth first search on a graph. And from the breadth first search, if all the vertices are visited, that means that the graph is connected. And The tree which is found from the breadth first search is known as breadth first spanning tree. So this is one of the use of breadth first search. Then we can also use depth first search. When we use depth first search, if we are able to visit all the vertices, that means we have they are connected components. All the vertices are connected, and the tree which we get with depth first search is nothing but it's depth first spanning tree. Now this is what we have heard about whether the whether the subgraphs are connected or not, or we have connected components or not, or we have connected vertices or not. There is another term known as strongly connected graph. Now, in the previous graph, if you see, it's not a directed graph. So we cannot say whether it's strongly connected or not. But if we look at this graph, it's a directed graph. What strongly connected graph means is from every vertex, we should be able to reach to any other vertex. Now, if you look at the previous graph, this one, what we have been seeing, this graph, this is not directed graph. So there is no orientation. So we can say that it is strongly connected because from every vertex, we will be able to reach every other vertex. But strongly connected graphs is, it's very difficult that every directed graph may not, to be a strongly connected graph, because directed graphs has orientations. Now, as the definition says, strongly connected graph is a graph in which all the vertices are reachable from any vertex. So if you look at this graph, is it strongly connected graph? Yes, it is strongly connected graph, and every vertex is visited. From every other, can be visited from every other vertex. If we start from A, we move to B. From B, we can visit E. From E, we can visit D. From D, we can visit C. If we start from D we can visit B. From B, we can visit E. Obviously, we can visit D again. Or from D, we can visit B. From B, we can visit E. Then from D, we can visit C. And from C, we can visit A. So if you look at this graph, any vertex, if we start, we will be able to visit any other vertex. This is known as strongly connected graph. Now let us look at another term known as, we have seen connected components, strongly connected graphs. Let us look at another term known as biconnected components. Now this graph we have already seen. I said that removing the edge from C to E will make this into two different components. Now biconnected components is nothing but we have two different components, one with A, B, C and D, the other one with E, F and G. Biconnected components is one or more components connected by two edges. Now this is not a biconnected component because it's connected only by these two connected components connected only by one edge. So it's not biconnected component. But suppose if we have another edge from A to E. So from A to E there is an edge, from C to E there is an edge. So there are two edges which are connecting the components A, B, C, D and another component E, F and G. So this is known as biconnected components. Now why biconnected components are important? Because if we have connected components there, that means if there is an edge C and E, if that edge is removed or that edge gets killed, then the vertices of the graphs will be separated. There will not be any way to reach from vertex of one component to vertex of another component. So this example is like if you have consider all the vertices as switches, network switches, and all the edges as communication lines. So if C and D gets edge gets killed, or that communication line gets killed, then there will not be any way to send messages from A to any other vertex, that is Z or E or F, in the next component. So that is why bi-connected components are very important. And to find bi-connected components, what we have is, we have to make sure that there will be two edges which is going to connect to different or one or more different components. So here what happens is, if one edge is removed also, there will be another edge through which we will be able to reach the other connected components. So likewise. Now let us talk about articulation point. Now this is theoretically, this is also very important. Articulation point is a vertex. Now we were talking about if the edge gets removed, we were talking about. But articulation point is a vertex whose removal results in connected components. Now in this case, if you see, if I remove vertex 3, C, there are 3 edges. When vertex C is removed, all those 3 edges also gets removed, because that vertex itself is dead, gets removed. Now what we are having is, we are having 2 different components, and then again there is the same problem of reachability. So articulation point is a vertex whose removal results in connected components. See, connected components means these 2 components are not connected. Connected components means all the vertices in this component is connected and all the vertices from this component is connected. But they are 2 different components. The same way, even E is an articulation point. If removal of E, if we remove E, then also we get 2 connected components. So in this graph, we have C and E as articulation points. But if we remove D, vertex D, is it an articulation point? If we remove vertex D, the graph is still connected. Then it's not split into components. So vertex D is not an articulation point. That's what the articulation point is very important in graphs, because it tells us where the vulnerability of node is. And it's used in many communication networks or in routing, and nowadays in routing, so and so. So this was about basics of some of the things in graphics and some of the terms in graphs.